to make as many, including myself, and we hope to make as many of these sessions available on our website following the event as our speakers are able to give us that permission. I'm Marin Clark. I'm a professor at the University of Michigan in the Department of Earth and Environmental Sciences, and I'm the lead PI of the CLASH project. I'm excited to talk to you about land surface hazards. They're more than just ground failure, so more than just landslides. They include sediment transport, river flooding, and our focus is really how they interact with one another. We're funded by a new EAR initiative, much like the efforts for the research coordination networks. The purpose of our project is to bring together the scientific community, ideate and strategize on how to make community level efforts that can advance science research in really big ways. And this effort is a part of solid earth science, but we've got some obvious connections to atmospheric science, social science, and engineering. But for now, we're really building out that science vision in solid earth and seeing how we build bridges to these other disciplines. So why CLASH? Why study land surface hazards? Why do we need that focus of study now? Well, we think it's pretty urgent. So this figure here sums it all up. There's a growing need and awareness of the impact of land surface hazards. It has in the past received a lot less attention than the seismic and volcanic counterparts. And you can see in the blue line here that the geomorphic hazards are predicted, or they have been increasing at a faster rate than some of the other major hazards caused by the climate system and the geologic system, so including earthquakes and volcanoes. And a large part of that has to do with the increase in severity and frequency of atmospheric events due to climate change. And with that, other changes to climate that exacerbate these hazards like forest fires, wildfires, droughts, and extreme precipitation events. But it also has to do with land use and urban expansion into areas where people were not previously living. And last, I want to point out that land surface hazards are ubiquitous. They touch most of the parts of most continents, not just the plate margins. So even some of the solid craton areas like the Midwest, where I live. And then there's been some growing traction, some recent US legislation, the National Landslide Preparedness Act that was passed in 2021, as part of a growing mandate to really prioritize the mitigation of land surface hazards. So what is CLASH? What is our project, these center catalysts? So year before last, NSF launched a new initiative in geohazards. And as a part of this program, they funded 4 trial centers, so trial research centers called Center Catalysts. And that's what we are. We're one of 4 projects funded. And that grant is to support pilot center activities and to prepare for a fully fledged center proposal. So one of those pilot projects is what you're taking part in today, our Modeling Expo. And it's also aimed to host community building events, much like the RCNs did, to bring scientific communities together. So the novel opportunity that we see to advance innovation in land surface hazards is to really understand, or really have a synoptic understanding of the hazard cascade. So the hazard cascade is not a new idea. It's been around for some time, and I've got a little cartoon here to explain what that means. So we have an event, a triggering event, which has a high impact. Following in time, that impact starts to decrease until other events occur. And because of the initial triggering event, those newer events are amplified. And so we really want to understand that interaction and how one particular event may set up more hazard downstream in the coming years to decades. And we think that that is an area that is really ripe for study, that has just started to receive a lot of attention and traction in our community. So here's a few examples of the hazard cascade. So one would be an earthquake, which triggers thousands to tens of thousands of landslides in the hill slopes. These landslides can dam rivers, causing outburst flooding, later even causing river aggradation and subsequent flooding events in the years to decades that follow. Wildfire is something that's rapidly changing our western states, dramatically altering the land surface conditions. And we know that those processes can accelerate erosional processes and alter carbon flux. And then another third example is with the cryosphere. So interactions with the cryosphere and its changes under global warming, and how those changes can lead to ground failure and flooding. So how do we approach this holistically? You know, what data are needed, what models are needed, and what connections are really the important crossover points for understanding how these individual processes interact and potentially multiply to cause hazard. Okay, and last, I just want to tell you a little more about who CLASH is. So I want to introduce our whole CLASH team. So we have 4 PIs, and we're joined on this call by all of them, the 2 Joshes, Josh West and Josh Roaring, along with Dimitrios Zekos. We have a really exciting and energetic steering committee, and we're supported by several staff members. In addition to the core Catalyst team, we have a number of partner organizations that are working with us that are directly involved with our pilot projects. And I'll call special attention to Albert Kettner at Systems, who has been one of our big partners on the modeling efforts that we are galvanizing. And then last, a really important part of our team are all of you. So a big, I would say the central part of these Catalyst projects are to really involve and galvanize the community. And so this means all of you who've taken your time out to join us today. We see your input as absolutely essential to both creating and crystallizing the ideas of what will carry us forward in our science. So we have an action-packed 2 days set up for you, and I am going to turn things over to my co-PI, Josh Roaring, who will tell you a little bit more about the concept of the Modeling Expo and get us started with our talks.
Great. I'll be brief. Thanks so much, Marin. Thank you all for being here. To put it simply, hazard cascades have become a thing. You see them in the scientific literature, the popular press, and once you define something, it really helps you to characterize it, quantify it, and make predictions. And I think that's why we're here today. This is the brainchild of our CLASH colleague, Dimitrios Zekos, who had the idea that we pull together all these process model components and get a sense of where we're at in terms of building a predictive framework. And thus was born the Modeling Expo. And upon a little reflection, it kind of reminds me of my upbringing in Minnesota, where you had a boat expo every year at the state fairgrounds, and you had canoes all the way to yachts. You could walk through, look at all these watercraft. You could even hop on board, imagine what it was like. And the whole point of all that was there's a lot out there, and there's no single boat that satisfies all your water going needs, and there's no model that satisfies all the model needs for the hazard cascade process. So we're not here to pick favored models. We're not here to hand out awards, but rather we're just here to get out a sense of the models that are out there, and together as a community begin discussing these disciplinary tools that we need to improve the prediction of hazard cascades. We have been presented with this challenge societally, and we hope that CLASH can be the intellectual hub for these activities. So thank you for the presenters that are here. The vast majority of folks you're going to hear from responded to our plea. They came to contribute their time and expertise. So thank you all. And thanks all of you for being here. We will not be successful in building this center without your ideas and your input, and that starts today. So thanks to the team and to everyone else who's here. A quick bit of housekeeping. One last thing is that this is the first part of our Modeling Expo event. We have an in-person event coming in the fall, and the details are going to be announced fairly soon on how that's going to work, but that's an in-person event. A little bit of housekeeping really quick is that the format of this is meant to be interactive. We didn't want to do a webinar just because we wanted folks to be able to jump in and discuss things as they come up. Everything is recorded here, and there's closed captioning. We anticipate folks are going to be able to pop in and out as the day goes on. So we will have some repetition of some of this material as we go forth over the next couple days. And so thank you for being patient with that. You can provide input in two ways. You can use Zoom chat, which we all are familiar with hopefully by now. We will also be posting a Google Doc chat that you can enter the Google Doc, and we will be priming you to do input material in there as well. Jill, one of our staffers, has many roles in the project. Today, one of her roles, and these are key roles, and one of her roles today is to keep us on task. So Jill is going to be pinning herself, and her Zoom screen has a timer, and each speaker will be held to the 7-minute timer, and it's going to turn yellow and flash when things are getting close, and the session coordinators can help keep us on task as well. But thank you, Jill, for doing that. If you have any questions or need for technological assistance, let us know. Adriana is reachable at that email address right there, or through direct chat. I did on my slide, I messed up the order of the events. Jane, thank you for pointing that out, so I apologize for that. We're going to start with the critical zone, and then we're going to move to geologic forcing, and then climate forcing. So my apologies for messing up the order there. So the other thing is we have a code of conduct, and that has also been dropped in the chat. So if there's anything out there in the Zoom world that is problematic, please let us know right away, and we will be tracking anything that we can help out with to keep everything keep running smoothly, and keep us on task. So with that, we are a bit late. I want to introduce Seulgi Moon, Associate Professor of the University of California at Los Angeles, who's leading us through this critical zone world. So Seulgi, thanks so much. Take it away.
Thank you. Thank you for a nice introduction. I will start sharing my screen, and okay. So everyone can see my screen? Okay, good. So critical zone, and today, thank you for coming to our session, the critical zone and near surface properties. So critical zone is basically a near surface layer where the rock, water, and air and living organism interact. So it extends from the top of the canopy here, and then also going down to the permeable bedrock. The deep critical zone is the layer, basically a geologic layer, including the soil and saprolite and weathered and fractured bedrock. Understanding critical zone is critical to assess the impact and consequences of land surface hazard. I took this photo from a few weeks after Montecito debris flow happens after the wildfire. And as you can see, the areas that on the hill slope has a lot of soils, and the debris flow itself is a mixture of the fine grained soils with the big boulders coming from the sandstone above. So these mixtures of the critical zone materials will affect the rheology of the debris flow and allow them to travel much farther downstream with a very gentle slope. Critical zone is important in multiple ways, but shown here in the diagram from Cliff Reeves' review paper, it allows the water flow through different layers of critical zone. And each layers will have a different hydraulic properties, which can affect the water flow and also affect the permeabilities and the porosity of these layers. And also critical zone will determine the mass flux that coming out of the critical zone, including soil layer and also the regolith, which is the rock with the degrees of any weatherings of chemical or physical weathering. There are multiple models to trying to model the different aspect of the critical zone, which here is showing a diagram of the soil productions and sediment transport laws. Based on the sediment transport laws, how the sediments or soil materials are moving down slope. And also recently, Leonard Sklar's group have shown that the combination of the initial sediment grain size, here shown as a latent grain size, and the weathering occurring within the critical zone can impact the sediment grain size distributions as well, which can be very important. And there are different models trying to explain the different degrees of weathering in the critical zone, which include topographic stress model, taking into account the subsurface stress distribution and the bedrock drainage models, the combination between the bedrock incision and the groundwater flow at bedrock, and then the frost cracking models, and also the reactive transport models. We don't have enough time to go over all of the models, but during today's talk, we will see a couple examples, which include my talk, and Rajaram's talk from Johns Hopkins University will introduce the physical and chemical weathering models, and Mong-Han from University of Maryland will show how we can use physical measurement to connect the critical zone properties with the hazard potentials. And also Miles Reed from University of Wisconsin will show an example of landscape evolution model coupled with the cosmogenic, and Dibiase from Penn State will show how the post-fire sediment delivery to the steep first order channels. So I'll move to my portion of the talk. So today I'll talk about the prediction of bedrock weathering based on the topographic stress model. This is based on multiple collaborations with many of my collaborators, and I'll present a brief introduction of this model. So first, topography can perturb the gravitational and tectonic stresses near surface. So you can see this idealized diagram of bowl-shaped ridges, which is calculated from the analytical solution of these two-dimensional ridges. That two lines are indicating the principal stresses. So this is calculated taking into account the gravity and horizontal compression, which is similar magnitude of the gravity, considering this relief of the ridges. And you can see the principal stress orientations and magnitudes are affected by the presence of ridges. As you go steeper, because of overburden, stress increases. So you can see the line length increases, which means stress magnitude increases. And also the stress orientations are pointing toward the ridges. This stress distribution will affect how the bedrock fractures are responding to the stress distribution at the subsurface. So our framework presented in 2015 was, if there is no topography near the surface, you will have a higher potential to have a shear failure. And near the surface, we also have higher potential for opening mode failure. Here I'm showing the based on the least compressive stress magnitude. And on the first column, I'm showing the failure potential, which is representing the shear failure potential. The second column shows the least compressive stress, representing an opening mode failures. And as you can see, near the surface, we have more potentials to have open fractures coming from shear failure or opening mode failure. And if you do have topography, depending on the horizontal compression, we may have different behavior. If the horizontal compression is less, then the stress distribution is largely affected by gravity. So in this case, below the ridges and below the valleys doesn't have large differences. However, if you do have a strong tectonic compression, the topography can perturb the stress field significantly. In this case, we expect under the ridges, the stress magnitude decreases and it can have a more open fractures under the ridges than the valleys. This can give us a testable hypothesis that the areas of the regolith or open regolith saprolite and also the open fracture zone, the shape of open fracture zone may differ depending on this stress conditions. So we apply this method to different landscapes, and basically the input parameters are including the physics of how the stress calculated, static. We are assuming a static equilibrium equations, and material property, including the rheology, including the Young's modulus and Poisson ratio and rock density. And we also take into account the geometry of boundaries shown in here that this is basically one of the examples that I use for the Golden Gulch on the Colorado site. So near the area that we are interested in, we have very high dense mesh, and further away, we do have a more larger scale meshes. So this area, we want to try to calculate more accurately. And then the most important one is boundary conditions of how do we constrain the ambient stress, which include the gravity and also horizontal tectonics. And we assume the surface topography is attraction-free surfaces. So the ambient stress condition is hard to constrain, but what we did is we compiled the existing compilation of in situ stress measurement coming from the hydrofracking experiment, then we can constrain the vertical gradient and also the horizontal compressive horizontal, most compressive and least compressive horizontal stress magnitude, and which will give us a boundary condition for the stress conditions. And then for my case, I used a boundary element model called Poly3D, and which can take into account the 3D topographic stresses. So here's the diagram showing that the conceptual diagram. So we assume a zero traction boundary from the surface or land surface. And this model has used for calculating stress perturbation from the fault movement. Instead of using it a fault, we use the Earth surface as traction-free boundary and calculate the stress perturbation, which eventually we'll able to calculate in the end. We can calculate the tensor of the stresses underneath of the surface, Earth surface. And those tensors, and we can calculate the two proxies, failure potential and the least compressive stress magnitude. And based on the field observations in certain locations, we can connect those stress proxies with the areas with the boundary between the weathered bedrock and unweathered bedrock. So in this case here, I'm showing theoretical calculations that I'm showing the isosurface of failure potential of 0.6. So the first top two rows showing the Earth surface with the same Earth surface, depending on the stress, horizontal compression stresses, this is weak compression, then we'll have a very similar isosurface of the failure potential. And if you do have very strong horizontal compression, we have a lot of perturbation, which will creating, sometimes the valleys will have more weathered bedrock and unweathered bedrock boundaries are closer to the Earth surface in this case. So that's why we do see an elevated isosurface plane under the showing in here. So we apply this method and apply to two locations. That one is Eastern Tibet. So first we use a 3D topography with the ambient stress condition, and we calculate the modeled subsurface open fracture zone. So in this case, we found the deep weather zone tend to accommodate a larger earthquake and precipitation-induced landslides in these cases. So we can make those connections in this area. And we also applied for another location, Coos Bay, Oregon. We explore the impact of the critical zone depth variations to coupled with hydrology models and the landslide models. And we show how the critical zone boundaries are impacting the water infiltrations and affect the locations of a landslide shown in here. And here's, I'll put the informations of the geomechanic software that allow to calculate this, the differences. In my case, I used the Poly3D, but they're more complicated models. Thank you. And I'll pass on to Rajaram from Johns Hopkins University to present about reactive transport models. Harry, can you share the screen?
Can you see my share screen?
Yes.
Okay. Thank you. Thank you for inviting me to do this talk. I'm going to talk about a couple process models for critical zone evolution. I start with some results from a previous modeling study that I did with Bob and Suzanne Anderson at CU Boulder when I was still there. A hill slope scale weathering model that couples hydrology, reactive transport, channel incision, and erosion. In this model, it's really the channel incision that is the initial driver of everything. Channel incision coupled with erosion sets the stage for the surface through which hydrologic inputs enter. And the hydrology in this model can include both vertical flow through the vadose zone and lateral flow beneath the water table. And we can calculate travel times along the streamlines that correspond to the hydrologic flow. So for example, in a dry climate, you would have long travel times going through the system. The travel time scale is on these graphs here. And in the wet system, in a wet end member, you would have relatively rapid travel times through this system. Reactive transport can be calculated along these streamlines in travel time coordinates that can be obtained by transforming from a velocity coordinate or spatial coordinate to a travel time coordinate. And when we do that, we can calculate weathering profiles. And because the weathering profiles are always initiating at the surface that corresponds to the ground surface that is evolved by erosion, essentially the model couples three sets of processes: erosion and surface processes, hydrology, and reactive transport. So with this model, we showed, for example, that in a dry end member, you have significantly long travel times. Correspondingly, you end up with a very thin near surface weathered zone, and which then has implications for other processes like landslides and other kinds of processes that this group is typically interested in. In contrast, in the wet end member case, you have relatively rapid travel times, which means that the weathering reactions proceed much farther into the subsurface, as a result of which your steady state weathering profiles might be having very, very deep weathered zones. And this difference is, again, something that has been predicted with stress as one explanation. What we showed in this paper was that you can get similar behavior with the influence of hydrology as well. This modeling approach, while it produces realistic behavior and can distinguish end members, like I've shown in this graph in this slide here, it does have significant limitations. First is that it uses highly simplified analytical solutions for hydrology and travel time. For example, employing unit gradient assumption in the Vadose zone and the Dibiase flow underneath the water table. That misses a lot of the complexities of subsurface flow that are relevant to modeling critical zone evolution over long time scales. And so one of the key things we're working on in ongoing work is to improve the model by adding several features that contribute to more realism. First is that we are using an unsaturated saturated computational flow modeling approach from pFlowTran, which is a widely used subsurface flow and reactive transport code developed in the DOE national labs. This allows for realistic representations of complex flow variability and also the deep groundwater flow, which is quite important in these systems. In the Dibiase flow system, you're basically assuming that the flow, there's really no flow below the stream, below the stream bed, for example, but a more complicated representation can capture the role of deep groundwater flow and upwelling streamlines. So for example, we can model a complex permeability architecture where you have a near surface zone that is more highly fractured and hence more permeable, a deep zone where the permeability is less, and calculate more complicated water saturation and streamline flow patterns, especially perched flow zones that are at this interface between the highly permeable and the low permeability zones. We can also incorporate complex subsurface architectures as resulting from stress controls. We can also handle permeability variation with depth, permeability change due to reactions, which is important in the overall process of transforming bedrock into regolith. pFlowTran also allows complex weathering reaction networks, allowing for gas transfer reactions that are driven by a gas exchange, which is either carbon dioxide or oxygen across from the air phase into the aqueous phase in the weathering zone. And in some of our future plans under the BCZN, the Bedrock Critical Zone Network project that Seulgi is also a part of, we're hoping to couple to geomechanics in a staggered coupling framework, incorporate stress-dependent permeability, which then allows us to make these calculations by coupling stress into the framework where we already have hydrology, reactive transport, and erosion. Just as an example here, showing some illustrative simulations of pyrite oxidation in a mountain hill slope system, where there is a contemporary weathering front at some depth below the surface that is shown here. You have an oxidized zone above it and an unoxidized zone below it. We can calculate, for example, the concentration profiles of dissolved oxygen, which is here the weathering agent, which gets consumed at some depth under the system, corresponding to the reaction products. The sulfate concentration profile shows the behavior that's seen in this graph here. And then we have a fairly complicated weathering zone here whose geometry is not 1D. It's a complicated 2D weathering geometry that we're able to calculate, which then has implications for how the rock turns into soil and it becomes available for erosive processes. In this framework, we've also been able to handle one aspect of mountain hydrology, which in many cases is snow melt controlled and hence has significant annual fluctuations, where you typically have dry seasons and wet seasons that alternate, especially in these cases where the weathering reactions are driven by some kind of gas transfer. The dry season is important for aeration, for supplying gases to the weathering zone. So the models that we are developing are able to handle these transient processes within a long-term evolution sequence also. And finally, we can also deal with discrete fractures as needed. In previous work from one of my former PhD students, we were able to do this and show how core stones can develop, which then can set a stage for a more complex representation of bedrock to mobile soil transformation processes. Thank you for your time.
Thank you, Hari. Thank you. And also we'll gather some questions in the end, and then we'll have a Q&A section in the end of the session. So please put it on the chat, Zoom chat, or in the documents that Jill posted. So the next speaker is Mong-Han Huang from University of Maryland, and he will talk about the geophysical method to constrain the near surface material properties.
Good morning. Thank you for the opportunity for me to talk about this topic. Let me just set up my time. Okay. So this is work in collaboration with a few folks in USGS here. So first, I just want to give a very quick introduction to critical zone, which is already introduced. So that's essentially the depth from bedrock or groundwater table to the ground surface. And then we can somehow link that to several different kinds of natural hazards, including landslides. So this is a numerical model that is actually quite similar to the previous talk, sort of in a wet condition, and this is done by Lebedeva and Brantley in 2020. So on the left-hand side, the red color, essentially what you're seeing is a ridge top to a valley bottom 2D simulation. The red to blue color represents from weathered bedrock to fresh bedrock. So if you think about whether bedrock can relate that to something like saprolite, so that's a weathered zone. The solid black line here is a groundwater, so you can see this transition from shallow to depth. On the right-hand side, that is the volumetric water content in this kind of model. So red means high water content. So you can see there's a clear heterogeneity in the vertical dimension. So in reality, we go to the field and then we drill boreholes. So it's represented by those two white dots. Then you can get the depth all the way to a fresh bedrock. You can also measure mineral depletion. You can measure water content, etc. However, to link between different boreholes, we typically just do interpolation. So similar to this 2D model, you assume laterally it is a homogeneous material. However, if you add some kind of heterogeneity, such as demonstrated by this paper, just here adding the vertical zone where you have a relatively high hydraulic conductivity, then when you run the simulation and you can see those subsurface groundwater flows start to have some kind of local concentration. So the arrow here represents a seepage forcing vector. So this lateral heterogeneity is going to give you some kind of local increase of pore fluid pressure. So that is going to increase hill slope instability. So in reality, how do they actually look like beyond those numerical models? So we first go to our field site in Puerto Rico. So there was tectonic uplift started roughly 4 million years ago. So currently the central Puerto Rico is higher than the north. In 2017, there was Hurricane Maria that generated more than 70,000 landslides. So here's a map showing you landslide density map. So more red, So more red means more landslide density. You can see the highest density is in central Puerto Rico in a town called Utuado. If you look at the topography of Utuado, you can see there's a plateau on the top and then the valley in the bottom. So if you focus on the region that has both the plateau and the steep slope, then here you are seeing the landslide distribution shown in the red. then you can see there's a lot higher landslide density on the steep slope than on the plateau top. The black circles represent the transiently points. So although you have more steep slopes on the side, but on the plateau, actually the slope is also very steep. So then the question we ask is what controls the size and type of landslide, and what is the weathering gradient across the different landscapes that can impact both the shallow and deep landslide and their style. So we have two sites, one on the plateau top, we call it Campo Rojo. The other one is on the steep slope, we call it Casa Boxer. So we introduced geophysical surveys that we did in spring 2022, including seismic refraction, shown on the left is Bill shows swinging the hammer, and also electrical resistivity that was shown on the right-hand side. And then we use a Bayesian framework for the inversion to get the seismic velocity as well as resistivity to the distribution. And because the model is sensitive to both porosity and the water content, so by using the joint inversion from both independent measurements, we might be able to better constrain those quantities. Then we can test those theoretical prediction that was shown earlier. So here's a result. On the top is Campo Rojo on the hilltop. The red to blue color represent low to high seismic velocity, with a contour line here shows you the VP velocity. So for Campo Rojo, you can see laterally more homogeneous, but vertically more heterogeneous distribution, with a very low velocity on the top and quickly transition to a high velocity, roughly 40 up to 40 meter depth. For Casa Boxer, you have a similar vertical distribution. However, laterally, you see a more complicated seismic velocity distribution. So if I draw two vertical lines to show you the velocity profile, it looks like this. The pink area shows you where we consider low velocity. So that's essentially velocity lower than 800 meters per second. You see that Campo Rojo has a much thicker low velocity zone. In addition to that, the low velocity zone, the velocity itself is actually lower than Casa Boxer. So we have some on-site cone penetrometer measurements for the top 2 meters. Here, black color shows higher value that essentially represent higher material strength. So those are on the steep slope. So it seems like we have higher velocity on the steep slope than on the hill plateau top. For the resistivity, then for the plateau top is relatively simple and also more heterogeneous for steep slope. So from this joint inversion, which I do not have time right now to talk about the detail, but you can see that on the porosity distribution for plateau, it has a much simpler structure compared to Casa Boxer. You may wonder why the value is so high. 80% porosity doesn't seem realistic. It is because we're assuming we know the mineral composition, and we're using bedrock mineral composition to calculate the bulk and shear modulus. So that's why the value may not be correct, but the pattern we believe will be somewhat realistic. We can also use this kind of model to calculate the water content and compare with a model setting that is different from our setting, but you can see some similarities, such as you have a high concentration at the boundary between weather to fresh bedrock. We also see some higher wetness value that might be coming from the precipitation that's going on almost every afternoon during our survey. I also don't have time to go to the summary, so I guess I will just let you read here, and thank you for your attention.
Thank you, Mong-Han. And then the next speaker is Miles Reed. He's a graduate student working with Ken Perrier in the University of Wisconsin. He'll talk about the landscape evolution models with the cosmogenic radionuclide.
Hi, this is the Casset supernova remnant. It's a producer of cosmogenic rays in our galaxy. And these can go on to produce in situ terrestrial cosmogenic nuclides on the Earth's surface, like beryllium-10 and quartz. And there's over 4,000 of these long-term denudation rates in existence. And these are often appealed to just in general site descriptions at this point in papers, because there's a lot of them. And TCNs have been wrapped into geomorphic models in the past, quite a few of them. And I'm just showing the landscape evolution model output from Mudd 2017, where he's showing erosion rate over time, where he's varying uplift rate in one and different parameters like bedrock erodibility in another, and comparing the apparent rate from beryllium-10 and what you'd get from just adding up the fluxes from the model. And these are different because these denudation rates are evaluated under a steady state framework, okay? So we wanted a richer representation of soils and hill slope transport in a landscape evolution model with cosmogenic nuclides, okay? So I modified Ferrier and Perron 2020 to make a novel model, and it starts out with a 2-layer mass balance, so bedrock and soil, where physical erosion is guided by nonlinear hill slope transport. Exponential soil production converts bedrock into soil, and there's also chemical erosion in the soil, the well-mixed soil. And all these processes in each cell can go on to change the TCN balance over here on the other mass balance, or the nuclide balance rather. And we track N sub S, which is the concentration of beryllium-10 or some other nuclide in the soil at the bedrock soil boundary, and also in a deeper bedrock profile, okay? And there's production and decay. And there's also transfer from bedrock to soil and lateral exchanges between soil cells. And the channels over here in the modeling domain can either be run in a static configuration where they're incising due to a lack of uplift rate, or from stream power incision. And this modeling domain is 150 by 150 10-meter grid cells on a raster grid. This is implemented in MATLAB, but can be run in GNU Octave as well. So we're interested in these transient responses because that's when denudation rates from TCNs can be wrong. So we're doing a perturbation experiment, and we're changing the uplift rate from 50 to 100 millimeters per 1,000 years. And I'm showing the actual and the inferred rate, and just little movies of these experiments. And here we have the actual, and the uplift rate change, the sort of relative base level lowering change, goes up from the foot slopes to the ridges in sort of a uniform pattern. And this is in that static channel mode, by the way. The inferred rate, D sub inf over here, is a little more hard to see what's going on. It's a little more diffuse. You do have signal shredding going on by the hill slope transport. And you can't really see the difference that well. And below there's some parameters, and they're all field derived, except for the bedrock, which is 50% plage and 50% inert, just to give a chemical erosion signal, which we do correct for in the inferred denudation rate, okay? So we visualize this with a new metric, ddinf. It's the inferred minus the actual rate, since we have both in our model. And we can see that in this tectonic disturbance, the ridges are at 0 nearly the whole time throughout this model run. And that's good for people that do point measurements of denudation rates, like soil production functions or long-term chemical erosion rates. But you can see in the hollows and the foot slopes, you do get large differentials. And that's from sort of relic material, if you will, being transported down into these areas subjected to hill slope transport. Okay, but does this matter for basin average rates? These are the ones that people that do all sorts of different work appeal to, not just sort of cosmo nerds. And it really is not, if we're doing this tectonic disturbance and looking at a sort of inferred basin average rate from a virtual concentration that we construct in the stream and sample every time step, and we take away the mean denudation rate of this little basin, the mean actual denudation rate, we also see that we don't see that big of a difference between the actual rate and the inferred rate through time, which, given our processes, we don't have like landsliding or in channel sediment storage or mixing. So little bit of caveats there, but it does show that this is a good method. It's robust to sort of perturbations because you're taking into account all the different production rates in a basin. The addition of stream power incision alters the response both temporally and spatially. As the incision wave kind of sweeps up into the landscape, you do get differentials along the foot slopes and in the hill slope hollows again. But along the ridges, again, you do see very low or zero d-diffs, meaning it is in local steady state. And down here, I do have some parameters for the like effective erodibility of the rock, and there's an incision threshold. But over here, we have the d-diff of the basin, and it gets to about the same magnitude, but it is offset in its timing. Okay. So I probably went exceedingly fast. I can't see the timer, but here's some take-home messages. Modeling TCN conservation on hill slopes in 3D is feasible at every point on the landscape. Ridges are close to local steady state, so where the actual equals the inferred rate during transients, tectonic transients that is. Basin averaged inferred rate reflects the current rate for uplift rate change, and stream power incision alters that response a little bit, but not too much. And this is the one I really want to drive home that for the natural hazards folks. TCN enabled models produce an output beyond topography within a process-based framework. So it gives you several things you can test against and maybe run some base level or baseline scenarios for your landscape to figure out, is my cascade or natural hazard cascade changing in some way? Is it different than the rate I'm getting from my denudation rate, my inferred denudation rate?
Miles, you are at time.
Okay, thank you.
Thank you, Miles. It's a great timing. Okay, and then we'll hear from Roman Dibiase about post-fire sediment deliveries.
Hey, so thank you, Seulgi, and thank you for the Clash team for letting me talk here. I have a talk I want to give here about post-fire sediment delivery in steep landscapes, and the video I'm showing here on the left is a pretty spectacular time lapse from a storm last fall in the San Bernardino Mountains, showing a series of post-fire debris flows that came out after the passage of Tropical Storm K through the region. And you can see a contrast between two places, one on either side of Yucaipa Ridge in Southern California here, of the sediment coming out of the landscape. On the left is mostly fine-grained and lacks sort of large boulders. On the right is from the same storm on a similar sort of steepness catchment on the north side of the ridge. Here you have, 2-3+ meter boulders in a totally different deposit style. And so what I want to get at with this talk is to try to understand how do we better predict the amount and size of sediment that's delivered from hill slopes to channels, in particular following fires. I want to emphasize a lot of this stuff is coming from work that Al Neely did during his PhD and during his postdoc with Seulgi Moon. And this work is funded from NSF, and we're relying on some LiDAR data that was collected by San Bernardino National Forest in Riverside County. And I'll show that towards the end, as well as NCOM. Okay, so this give you a sense of the study area here. We're in Southern California. We're going to focus on the San Bernardino Mountains for most of it today, but also bringing in work from the San Gabriel Mountains and San Jacinto Mountains. And when I first started working on this problem after the 2009 station fire, this was the landscape for pre-fire LiDAR coverage in 2009. If we fast forward to 2020, the things have changed a lot, and this is really providing this unprecedented ability to now track how landscapes are changing before and after fire, and moreover through time. So we're able to track sediment through time at the catchment scale at high resolution. The areas I'm going to focus on today are a series of fires that happened in summer and fall of 2020, the El Dorado fire and Apple fire in the San Bernardino Mountains, and the Bobcat fire in the San Gabriel Mountains. The question I'm asking here is, how does sediment get from hill slopes to headwater channels? In background, you can have sort of debris flows that form without any fires in these steep landscapes. These are a couple examples on the left. After fires, you can have mechanisms like rilling or post-fire dry rabble loading of channels that accelerate this process of getting material off of hill slopes and into channels. The time lapse on the right here is showing a channel that loaded up with fine sediment following fire, instantaneously following the fire. And then after a pretty moderate storm, cleared out down to bedrock. This is the process that I'm interested in showing here. And we're going to connect this in terms of the volumes and the size contrast with the pre-fire data. To look at the size distribution of material before fires, this is work from Al Neely's PhD, where we tried to map out sort of how sediment gets off of cliffs and into channels by mapping bedrock fracture patterns on cliffs and connecting that to measurements of grain size distributions throughout channel networks using high resolution imagery. The thing I want to highlight here is that if we look across landscapes that increase in steepness from fully soil mantled to mostly bare bedrock, one of the surprising things that came out of this work was that once you get like 15–20% bare bedrock on the hill slopes, the surface grain size in the channels gets pinned by the bedrock fracture spacing. And so it doesn't take much outcrop on the hillside to really coarsen the material in the channels. This has implications for thinking about the sensitivity of these landscapes to changing their grain size following fire with the loading of dry rabble. If we look at one of these patchy landscapes, and by patchy I mean sort of a mix of soil and bare rock, we can partition the landscape into different sediment sources based on the local slope. And we can see sort of 3 different regions here in this landscape. At the lowest slopes along the ridge lines, you can still see ash preserved, showing no erosion. These are sort of stable soil mantled slopes, less than 35 degrees. At steeper slopes, you have soil that gets released from behind vegetation after burning and gets delivered directly into channels after fires. And this is what process we call dry rabble. On steeper slopes, say steeper than 45 degrees, are characterized by bare bedrock. And each of these different components of the landscape produces a different characteristic size distribution of sediment. So this is work from Al, who went out and mapped out the grain size distributions of these different parts of the landscape. The cliffs you can get from the fracture patterns exposed on the bedrock cliffs, and put together a mixing model that takes the partitioning of the landscape into the different process domains, the grain size distribution from each one, and then make some assumptions about how you weight the flux for these post-fire observations to get a final sort of mixing model. The thing I want to highlight the results from this work is that comparing this to pre and post-fire channel grain size data that we had in the Yucaipa Ridge area, we found this interesting dynamic where at low slopes, the grain sizes are fine before the fire and after the fire. In the steepest landscapes, the grain size is coarse before the fire, but there's not much source for dry rabble, and so the grain size is coarse after the fire too. And in intermediate slopes, you get this dramatic fining where you resurface coarse grain channels with fine grain material, and this leads to increased debris flow hazards. We can make some connections between the observations of the debris flows that we see following fires. This is just showing two cases that I showed in the opening slides, how we think we might be able to start explaining these contrasts by the surface expression of soils and bedrock. The other piece of this is mapping out dry rabble loading volumes. We can do this with repeat LiDAR, and I just want to finish out with this slide here that's showing sort of how we track sediment through time in 2 parts of this landscape, one that had a high dry rabble loading signal and one that didn't. And you can kind of see on the left here the sort of inflating of the landscape through time. We have 4 cycles of LiDAR that we're able to start tracking how sediment's moving through the landscape. And the differences in the sediment grain size impact how these landscapes respond to storms. Thanks.
Thank you. Thank you, Roman. It's a spectacular images with the sediments. So we are finishing these sessions, but we wanted to have a Q&A discussions for the panel discussions in the next 7 minutes. So there was a couple of questions posted on the Google Doc. So the 3 questions that we had was, first one is, what are the opportunities for model coupling to address hazard cascade? Second one is, what model areas need attention? What are the central knowledge gap? And third question is, how does modeling inform data acquisition and sensor deployment and development? The first questions, maybe we can, I want to have some discussions with the speakers that what are the opportunity for the model coupling to address hazard cascade? One question came in that the Hari's talk and Mong-Han's talk indicating the water and weathering is really important. And then how does that actually impact the fracturing of the rock that is relevant to my talk, and whether we can have a potential to link hydraulic models with the stress and fracturing and the weathering models. So there's any speakers have some insight on this?
Yeah, if I may chime in, that's a great question. I think that a lot of these processes that we put into the models are phenomenological in some sense. But underneath there is a relationship between the degree of weathering and some kind of a strength parameter. And exactly how we can relate that to actual, real strength in the mechanics sense, that's a completely different, it's a different question. It's a much more challenging question. There is a class of models that deal with, like the damage type models, that where you can actually calculate a damage variable as a function of other processes. That may be one way of going at this, but then you would have to sort of develop some kind of constitutive relationships based on observations before you can use an approach like that.
That's a very good question. And actually related to the third questions that comes that what are really how we can do data and the model compositions, combinations, and related to Mong-Han's talk as well, what are the minimum or what are the really critical data to actually inform the model and expand the CZ transitions into the 3D? Maybe Roman and Mong-Han and others can chime in. What do you think is most critical data to give us more information about CZ?
Well, I guess I can just start. I think just like the presentation I gave, that the conventional modeling has more like a 2D homogeneous type model. So, but locally we have change of rock type, we have, maybe uneven distribution of groundwater, etc. So that can really generate some kind of horizontal heterogeneity. So one thing I found from this Puerto Rico is that on the steep slope, because of weathering is more uneven, so you may have more locally increase of pore fluid pressure, then that might drive those shallow landslides to occur compared to those on the hill plateau top, because it's very quickly removing water, so you cannot build up the pressure as easy as on the steep slope, even though it's also very steep. So I guess for future might be this modeling where you can really more in consideration of those lateral heterogeneity.
Yeah, I'll just add that for the surface cover and the heterogeneity and surface expression, I think one of the opportunities now is that we can just directly measure things in terms of hazards. So if we can track sediment patterns following fires directly with repeat LiDAR, there's obviously needs to understand the mechanisms for how you actually generate that heterogeneity. But from a practical standpoint, I think there's also just a need to how do we ingest large quantities of data, directly measure things like patterns in bedrock exposure or patterns in sediment loading directly.
Anyone want to chime in? You can raise your hands and then we'll let you speak. So there is a Zoom that there is a raise your hands button, and we can also go in that you're right that the spatial. There was another question about spatial variability of material property imposed by critical zone seems critical to understand hazard. Can model can help inform how to quantify such variabilities? To some degree, maybe yes. So we can predict some degree, but I think Roman is right. We need direct observations or direct measurement to compare with the models, because we can predict anything that if that doesn't work with the reality, then that may not be most invaluable informations in that case. So in that case, I was wondering that even though I had a work with some sites with abundant information, that the heterogeneity is super high. The soil depths this heterogeneity is just unbelievable. That So how do you anyone like maybe Josh also have a lot of experience on the data field locations too? How many data we actually need, or how can we do plan better in area? Maybe as Mong-Han site shows that some area we do know that there is a lateral heterogeneity, that means that we need more data to do those. But some areas we know that there's not very much, then maybe we don't need as much as data. But how can we do combining the practical point and the scientific point? Anyone can give some insight will be appreciated.
Well, I want to say the measurements are not easy. They are very valuable, but my feeling of where measurements and modeling come together is that you can't measure every system, but if you can measure some representative systems at high resolution, say in the same type of geology, and then use models to learn from that and extrapolate across the entire landscape, that might be where the two come together.
Mm-hmm. Mong-Han? You're muted. Mong-Han is muted. Can you someone
Sorry,
unmute?
I thought I
okay.
unmute myself.
Uh-huh.
Right. So a lot of time we go to the field, do a direct measurements after the event, the disaster has happened. So I was thinking that in the long term, if we already have products like USGS has those like landslide potential maps, or a lot of hazard forecast map. So I was wondering if we already know a rainstorm or something is about to happen, then we can have sort of like measurement before, during, after. So we can probably get some very valuable data about landslide initiation and how different types and how they were driven.
That's very good point. And Roman's work actually shows that using the size LiDAR data, we know where the rebel loaded on the channels. That was really interesting. Maybe if the next rainfall comes, then maybe the area that has a lot of the reflow potential. So from there, that was the last question. So I'll hand it over to the second section to Ben.
I'll jump in really quick. I want to first thank Seulgi and the speakers for kicking this off in an amazing fashion. That was spectacular. I was jotting notes down obsessively during that. I think the questions are great, dealing with heterogeneity and how far we can get with some models before events is fantastic. And, it's worth asking, how wrong will we be if we pulled together some of the models we just heard about to look at weathered zones, look at soil thickness, and look at channel loading and so forth. So I think the framework pieces are starting to come together. Thank you all for getting us going. Without further ado, though, I want to transition to our geologic forcing session, and Ben Mason is